Once again, we've applied power to our lasers, and we've activated the argon laser with a power of just under 20%. Now we will go up to our Acquire tab and click on that, and now we can activate our lasers on the main screen. It is on this screen that we can turn on the laser that we're interested in working with, and as you can see, when I click on the tab for the UV laser, the red light indicates the laser is powered up, and a line comes down showing that a laser line is being generated, and this line comes down to show me the dichroic mirror, which we'll talk about in a second. But if you look on this spectrum, you'll see that on the visible spectrum we now have a single laser line of 405 nanometers. If I turn the laser, the UV laser, off, that laser line goes away. Now from time to time you might turn on the laser and not see a laser line on your spectrum. All you have to do is double click on it and the laser line should come up. So that's the UV laser. However, we may also want to work with a visible laser, and so we click on this tab and again you see a red light come on. However, no laser lines are displayed on the visible spectrum using the visible laser. The laser lines only come up when we increase the power on the visible layer. Here you see that I've increased the power on the 458 laser line to 3%, and a laser line shows up at 458 nanometers. I can do the same with 476, 488, 514, 543, and 633. And so you see rather quickly that we have 7 laser lines that we can use to illuminate a whole host of fluorophores, everywhere from 405 nanometers on up to 633. It is very important when you're using the confocal microscope to keep the laser power low. A rule of thumb is to keep your laser power below 10%. If you increase your laser power, you are using the laser more than it possibly should be used. You may be wearing out the laser a little more quickly. You're certainly generating more heat in the laser bank, which is not good for the lasers. And you run the risk of photo bleaching your fluorophore. So as a rule of thumb, try to keep the laser power very low. There is a way to accommodate the brightness of your image without increasing your laser power, and I'll show that in a minute. In order for the computer system to gather images off the microscope, the computer has to digitize the image that it sees. Digitization is the process whereby an analog image, which is captured by the microscope, is converted to a digital image in the computer. To illustrate how this happens, let's talk about your camera phone and how your camera phone can digitize an image that it sees through the optics in the camera. The camera phone has a small set of optics built into it, and the image is passing through the optics and it's hitting a sensor, a CCD sensor, which is essentially a chip which is sensitive to light. As you can see, this is a live image, but at some point when you want to take your picture, you push a button and your image is digitized and captured in the phone. The computer essentially does the same thing that your camera phone does. However, instead of a simple set of optics, we have very sophisticated optics in the microscope. Instead of a simple sensor that may take a 1 megapixel image, we have a system that is highly sensitive and can take upwards of 20 megapixel images. What is a pixel and what is a megapixel? A pixel is a picture element, and we'll explain more about that in a second. But a megapixel is 1 million pixels. So if you have a megapixel camera, you are shooting an image recording intensity of light and color with 1 million pixels or picture elements on your digitizer sensor. In order to show this more effectively, let's minimize the LASAF software for right now and focus on an image that I have on a screen. This is a digitized image that was taken with the microscope using the confocal software. You can see the different colors of green and black with the background, and you can see that there's different intensities in this image. If we magnify this image, you will see that we can get to a point in magnification where individual pixels become apparent. Here you see what was once a round circular object, and we're seeing it highly pixelated. Each one of these little squares is a pixel. Each pixel records not only the intensity of the light that's hitting it, and you can see a difference in intensity from this pixel here and say this one over here to the left, which is darker, and it also records the color. The system has the ability to record about 16 million colors in high resolution format. And so when we zoom out on our image, we'll see that the pixels go away and the highly resolved image with a lot of detail shows up. This is the process of digitization, where you're capturing an analog image off the microscope and digitizing it in the computer so you can display it, study it, look for boundaries of brightness, do area calculations and such on your image. Let's focus on the acquisition mode tab, and we will talk about sequential images and mark and find at a later date. This has to do with repositioning the stage to find objects of interest. But the important thing to remember from this tab is that we should start out in XYZ mode. That means that we're going to be recording images in X and Y and in Z, which is focus. So we're going to gather three-dimensional images under the XYZ tab. We could select other options for recording images. For example, we could do X imaging with time. So we can do a time-lapse image on the X-axis, or we can do X and Y and time. So the system will allow us to do time-lapse over X and Y, and even X, Y, and Z and time. We can also do scans for lambda, which means we are scanning in X and Y for a particular wavelength. So you can tell the system to only scan in X and Y looking for a particular wavelength and ignoring all other wavelengths. This tab is very flexible in terms of the scans that we can start, but let's continue with XYZ. The other tab that is very important to use is the XY acquisition tab. Again, we showed you how to minimize that using this arrowhead, but for now we want to keep this open. On the left here you see that it gives us the format in resolution in terms of the number of pixels that we have in our digitizer tablet. In this case it defaults to 512 pixels across and 512 pixels down. This is a great place to start to begin your imaging, but as you can see, we can select from a whole host of various resolutions all the way up to 8,000 by 8,000 pixels in X and Y. But we'll talk more about that later. For now, we're defaulting to 512 by 512. You also see that there's a speed tab. This allows you to enhance the speed of the digitizer, or the speed at which it captures images. This actually controls the speed of the mirrors in the scan head, very tiny, very precise mirrors, and here we're defaulting to 400 Hertz. Normally we'll work at 400 Hertz or 700 Hertz, or in some special cases we might work at 1000 Hertz. Notice that when we select 1000 Hertz and higher, a zoom function engages. Let's go back to 512 by 512 at 400 Hertz. And our zoom factor should be down at 1. What is zoom factor? Zoom factor is not true zoom in that you're zooming in on an already established image. In fact, the zoom factor actually allows you to look at a smaller and smaller and smaller portion of the digitizer tablet. So it's sort of a misnomer. We're not actually zooming in on our image. But normal zoom factor is 1. However, when you increase your speed to 700 or 1000, the zoom factor goes up a little bit. You saw it go to 1.7 on 700 megahertz, and you saw it go to 3 on 1000 megahertz. And so you need to keep this in mind. As you increase the speed of the digitizer, you're looking at a smaller area of your image. So keep that in mind as you manipulate the speed on your digitizer. But for now, we'll keep it at 400 Hertz. There's also a box that you can click on, and you can control zoom manually with this tab, or you can type in a zoom factor here, and the system will zoom to that factor. But we're going to leave it at 1 for now. There's also a group of arrows here, and this allows you to move around an already digitized image, which you'll see in a second. If you want to go back to the center of the image, which you already acquired, you press the center button. Finally, on the left-hand side bottom of this tab, you'll see that we can do a line average and a frame average. This allows you to reduce noise in your image, and we'll come back to this in a second. The pinhole box allows me to select that, and then it gives me the opportunity to change the size of the pinhole. What is the pinhole? The microscope actually has 2 different pinholes. One pinhole is right after the lasers, and so you're controlling the amount of illumination that comes out of the laser, and the other pinhole is right after the objective. So you're controlling the amount of information that comes from the objective. Only one of these 2 pinholes can be changed. The pinhole after the lasers is static and it cannot be changed. The pinhole after the objectives can be changed, and it's another way of brightening your image. However, remember that by brightening your image, you're allowing a lot more light into your image from your microscope, and you could be hurting your image and reducing the ability to resolve small structures. Generally, the pinhole is set by the software, but as you see, you can click on pinhole, and then it will allow you to change the size of the pinhole. We'll discuss more about this later. For now, let's leave it unchecked. The other box that you can check here is called bidirectional X. The system, when it scans an image, scans in X, and then it drops down and scans in X again, it drops down in Y and scans in X again. Normally it scans from left to right in X, it goes back to the beginning of a next line of pixels, scans across those pixels, goes back to the next line, and so forth. You can change it to bidirectional, so that the system will scan in a line in X, drop down, and scan backwards, and so you can increase your speed by using bidirectional scanning. This, however, can also increase noise in your system. So for now, we'll leave it checked off. Once again, we can enhance our image by doing line averaging. What is line averaging? Line averaging allows me to take more than one scan per each line, and then I average out the values of that line, and I get a cleaner, crisper, less noisy image. Normally, I would select 1, but in some instances where I have noise, I may want to go to 4 or 6 and do line averaging for each line that I acquire. Remember, however, that when I increase the number of line scans that I do per line, I'm slowing down my process. My 4 may be photo bleached more because the laser is hitting it with more light, and so it's a trade-off. You want to get the crispest, cleanest images that you can using line averaging, but remember that you run the risk of photo bleaching your specimen. For now, we'll leave it at 1. You can also do frame averaging. What is frame averaging? Frame averaging allows you to take multiple frames. 2, 3, 4, 12, or more. By the way, on both of these pull-down menus, you can specify by clicking on the bottom the number that you want to enter. If you keep clicking, you'll reach the end, and then there's a user point that allows you to enter the number of scans that you want to input. But again, the more frames that you scan per image, the slower the system will become, and the more you run the risk of photo bleaching your specimen. So we'll leave it at 1 for now. This final tab allows you to rotate your image around a point in the center, but normally we'll just leave that centered at the center point of the travel.